Hello everyone, this is Dr. Jenkins, and Dr. McLean here is with me in spirit. This is going to be the video for our two virtual laboratories, one of which was lab number 6, effective carbohydrates, and one was lab number 7, thermoregulation. So to make up for these labs and do it virtually, here's the ask. Each student should watch this video, and then you're going to have access to a handout on Blackboard that you will then be able to look at all of the data and answer questions. And as always, we are here if you have questions as you do the assignment. But here's the introduction. So 2 labs, all right? These labs together are going to comprise 3 different portions. And I got my fancy little trusty pen here. Part number 1, let me change colors, see if I can maneuver this properly. Part 1 is looking at the effects of drinking a carbohydrate beverage during a long activity. Part 2 is looking at the effects of a low carbohydrate diet on exercise. So our first 2 parts are looking at carbohydrates. The first part is looking at whether or not you drink some Gatorade basically during the long exercise. And then part 2 is looking at what if an athlete had a high carb diet and what if they had a low carb diet. And to make things a little more interesting, we're going to be comparing for these parts, part 1 and part 2, we're going to be comparing a trained individual, aka Mr. Usain Bolt, hello, versus a sedentary individual. So we're going to be looking at the influence of carbs on exercise and comparing real data from a trained person to a sedentary person. So exciting now, isn't it? The third part, apparently I'm still figuring this out. The third part is looking instead at thermoregulation. And to make things more interesting here, we'll stay with black. To make things more interesting, we're going to be looking at how the body thermoregulates during exercise in men versus women. So battle of the sexes. So that's the outline. Okay, the first 2 parts deal with carbohydrates. So we need to make sure that we do a bit of a review. I know that you already know this stuff because I know that I covered it in lab, and so did Dr. McLean, and so did Dr. T. But just to make sure we're all on the same page, we remember carbohydrates. We remember that there are simple carbohydrates. And we remember that there are complex carbohydrates. This should be a nice, easy review. The simple carbohydrates, we had the monosaccharides. Monosaccharides, the prefix mono tells us it's 1 sugar. An example of a monosaccharide is glucose. And then we have disaccharides. The prefix di tells us these are 2 sugars. An example of a disaccharide is table sugar or sucrose. A complex carbohydrate is known as a polysaccharide. Poly means many. So instead of having just 1 sugar or 2 sugars, a polysaccharide has 3 or more sugars chained together. So many, many, many sugars. Some examples of complex carbohydrates: starch, fiber, glycogen. We all remember the function of carbohydrates. Of course, carbohydrates serve as a big energy source, but I want you to be more specific. Carbohydrates is what our cells go to first. So it's our immediate energy source. Because as we know, our cells are going to first go to carbs for energy, but over a little bit of time, they're going to start to burn fat also. And from there on, you're burning a combination of carbs and fat. But at first, because we can break them down and metabolize them most quickly, our immediate energy source, carbs. We also remember the acceptable macronutrient distribution ranges, the AMDRs, your favorite. And so we know somewhere between 45 to 65% of our diets should come from carbohydrates. Isn't this a great review? Now let's take it to the next step, because Today's laboratory is looking at carbohydrate ingestion during activity. But here's the rub. Does every athlete need to be drinking buckets of carbohydrates during activity? The answer is no. How do we know? We have a pretty good guideline, actually. If you are exercising for 45 to 60 minutes continuously, then and only then do you need to consider bringing in carbohydrates during activity. During. I can guarantee this is probably going to be an exam question. Only if you're exercising for 45 to 60 minutes continuously do you need to bring in carbs during. If it's less than 45 minutes, you do not need to bring in carbs during because you have enough carbohydrates in your blood and your muscles. So, let's just ask ourselves a couple questions. Does carbohydrate intake influence athletic performance? Of course it does. Why? Because carbs are our cell's first energy source. So we have to pay attention to carbs. Does every athlete need to drink buckets of Gatorade? I said no. Let's say it again together. Say it out loud. Only need to think about drinking some sugar in during activity if it's 45 to 60 minutes of continuous activity or more. Is a low-carb diet good for an athlete? Pretty crazy that I'm even asking this question. The answer, of course, is no. Because, same answer as the first one, carbohydrates are a big energy source. This is particularly a good topic to talk about now because the keto diet is popular. Keto, meaning that we purposely lower our carbs and increase our protein intake and fat intake, thinking that if I don't have as many carbs, I will burn more fat and therefore burn more fat and get more energy from that fat. But for an athlete, no. An athlete needs carbs as well as fat. Okay, let's move on to this lab because this lab is pretty cool. We've been talking about all these things. You've been talking about it with Dr. Thompson in a lecture, but I want to talk about the data. This is the beauty of a lab. We have the data. For this laboratory, these two labs, we're using a virtual type of physiology program. You might think, oh, virtual physiology, maybe it's like a video game. I suppose from our vantage point, we're just pressing buttons and getting data. But what I want to point out is I want to make sure that you know that this data is real. So some people really went on a treadmill, put a bunch of EKG leads, put a bunch of tubes in their mouth, shoved needles in their finger while they were exercising to get blood. So the data that we are getting is real. Real data. That's exciting. Okay, so as we talked about, 3 parts of this lab. The first part is looking at the effects of carbohydrates during prolonged activity. And as I said before, we're comparing a trained person to a sedentary person. In this case, we're looking at a 25-year-old female endurance athlete. So a 25-year-old female endurance athlete really got on the treadmill, and we got all this data. And then we had a sedentary person, also a 25-year-old female, right? We really had a sedentary person get on the treadmill, and this data is real. They were put on a treadmill, and they were told to run for as long as they could. Here's what the program looked like that we're using. So when we use the program here, what you would have been doing in lab if we were meeting in person is you would have selected your athlete. So let's say we're doing part 1 here. We would have selected a 25-year-old female endurance athlete. We would have then selected our 2 conditions because we have 2 trials. If we want to look at the effect of drinking carbohydrate drink during exercise, we have to also see what happens when you don't. So in trial 1, this person did not bring in any fluid. And that's what this picture is showing you. When I set up this data for the first thing, it was a 25-year-old female, and then it was no fluids given. We also ran the same trial with the same athlete, but in the second trial, she was given a sports drink every 15 minutes. Okay, after we set it up, we chose our athlete, and then we chose variables. Again, ladies and gentlemen, real data. So we chose our athlete type and our condition, and then we selected what variables we wanted to measure. So for this first trial, this first part, we measured all these things. So you can see I'm showing you a picture of where I clicked that I wanted to get the data for cardiac output. All right, so now we've selected our subject and test condition, we selected our variables. But before we do that, before we get to the real results, we have to talk about what these variables are. So there's 4 variables. Make sure that you review these. We've talked about some of them already. Cardiac output, volume of blood pumped out of the heart each minute. Keyword there is per minute. Respiratory exchange ratio, you know all about this. By doing some simple division with the amount of carbon dioxide we produce and the amount of oxygen that we take in, we can tell from the RER what nutrients our muscles are burning for fuel. And these should all be a review. From this exercise, we're also going to get blood glucose. So we take a blood sample, we can see what is the amount of glucose that is circulating in the blood at that time. And when they put these subjects on the treadmill, they were also able to measure muscle glucose uptake. So not only does it matter how much glucose is in the blood, we have to be able to bring that glucose into the muscle. So make sure you review those. So here we have our results. Really cool, this program. I'm a little bit bummed that you're not going to be able to experience it for yourself. Couple things. Over the past couple of years, we've named our trusty 25-year-old female endurance athlete. We have named her Greta. And Greta did a lot of work for us. And while she was running, remember, she was told to run as long as she could. So in trial 1, so remember, let's go back. Remember trial 1. Trial 1, she had no fluid. Trial 2, she did have a sports drink given. All right, trial 1, she was no fluid. Trial 2 was fluid given. So after we let her go, we can see the results here. This happens to be the results from no fluid given. So without bringing in any carbohydrates, she was able to exercise for 120 minutes. Remember, she was told to run for as long as she could on the treadmill. That's pretty solid, everyone. 2 hours. I mean, think about how well you would do for doing 2 hours on a treadmill without any kind of sports drink. So Greta did a good job. From this, let me actually go back. From this, for whatever variables we selected, it gave us her real values. And we got resting values, and then we got values at 10 minutes, 30, 60, 90, and 120 minutes. In the handout for you, we have put them in a lovely little table, all right? And remember, we want to compare sedentary to our endurance athlete. So in this answer key here, anything in blue is the endurance athlete. So all the values that are listed first are the values that were obtained in the endurance athlete. Anything that's red are the values that were obtained in the sedentary. So what do you see at rest? At rest, there was no difference between the endurance athlete and the sedentary person in cardiac output, RER, blood glucose, or muscle glucose uptake. But of course, as time went on, there were differences. And what's fun for you is you're going to be comparing these results and you're going to be answering questions. I know you're excited. So you really do want to pay attention. For example, this is trial 2 with the fluid intake, and this is trial 1 without. One thing to look at, in which trial, without fluid intake or with fluid intake, did our endurance athlete and sedentary person exercise for longer? Well, we can see that with fluid intake, our endurance athlete, blue, exercised for 150 minutes. Without fluid intake, How long did our endurance athlete go for? 120 minutes. And actually the results were different. Oh, there's my dog, Allie. Sorry about that. Sometimes it keeps kicking me off. We're just going to open it up again. Okay, the reason why we can't just go with it. Let me go all the way down to where we were. There's Greta. Okay, so when you get your results, they're going to be different for the endurance athlete versus the sedentary person. Good luck with those questions, ladies and gents. Okay, our second experiment. The first one was looking at what were the differences in performance when we didn't drink anything during the exercise versus when we did drink a sports drink. The second part 2, looked at the influence of a low-carb diet. Again, we think we know what's going to happen. A low-carb diet is bad for athletes. But I want you to see the data. I want you to see how bad it is so that you can pay attention more, because it does influence. Again, we're comparing a trained to sedentary person. Same setup as before. 25-year-old endurance athlete, female trained, 25-year-old female sedentary person. Both were put on a treadmill, asked to run for as long as they could. So here's our 25-year-old female endurance athlete. In trial 1, our female athlete, for the week before, had been ingesting what we would expect, about 60% of the diet from carbs. That's a really good amount of carbohydrates for an athlete. And then in trial 2, a couple weeks later, same athlete came back in, but this time she had been eating only 40% of her calories from carbs. And here's our virtual setup. It's our 25-year-old female endurance athlete, and she's on a low carbohydrate diet. For this one, we looked at some different variables, because why not? 3 variables we looked at: RER, muscle glycogen, and rating of perceived exertion. Make sure you review what those are. RER, we already talked about. Muscle glycogen. We may remember glucose is a monosaccharide circulating in the blood, but glycogen is the stored form of sugar. It's a polysaccharide. So not only do we have some glucose in the bloodstream circulating just by itself, we also have some stored sugar in our skeletal muscles, in our liver, as a storage reserve. And we're actually able to measure that. You may be wondering, hey, Dr. J, why on earth is this soil sampler here? I'll tell you why it's here. When we actually put someone on a treadmill, in order to get muscle glycogen, that's a really invasive, we have to actually take a device that looks similar to a soil sampler. And while the person's on the treadmill, we shove this into their quadricep. And then we pull out the top. And what we get is a sample of the muscle tissue. Not obviously as big as that, but I wanted to make a point. Very invasive. So perhaps if you're ever asked to participate in an exercise physiology study, you may want to ask what it is they're going to measure. Because if they're going to measure muscle glycogen, they're going to be stabbing a soil sample-like device into you. Now, if you're like me, you would do it for the name of science, but I'm just saying. So review that. And then rating of perceived exertion is a subjective measure. So while the athlete and while the sedentary person is on the treadmill, they simply ask, how hard do you feel like you're working? If you feel like you're not working at all, you would say 6. If you feel like you're working as hard as you possibly could, you would say 20. All right. So here's our results for Greta, right? So we said whatever variables that we looked for. So we wanted to test for RER, muscle glycogen, and RPE. And then on your handout, you will also get the results that look like this. Similar to before, what's listed in blue is our endurance athlete, and what's listed in red is our sedentary person. What's unique about this one, unlike the first thing where we had a trial where someone didn't drink carbs and a trial where they did, in this one, the values are different even at resting, particularly in muscle glycogen. So having a reasonable needed amount of carbohydrate can even affect your resting value. So how do you think this person's going to do when they're on a low carbohydrate diet, when they've got such a low storage of glycogen to begin with? There's also a big difference in how long they were able to work out for. So just like before, these athletes were really on a treadmill, and they were told to go as long as they could. Look at how long they were able to go when they had had an appropriate amount of carbohydrates in their diet, and look at how long they were able to go on a low-carb diet. Big difference. Okay, so you're going to get to go to those questions again. Yay. All right. The last thing that we did in these virtual labs, instead of looking at carbohydrates and exercise, we're talking about thermoregulation. Our body's ability to balance heat. In the case of exercise, how to get rid of the heat that we produce. Let's talk about this first. I always like to talk about this just because I want to show you how crazy people are. You all think I'm crazy? Not as crazy as some. Maybe you've heard of ultra marathons, ultra distance running, 50-mile race, 100-mile race. There's a Leadville 200-mile run. Can you imagine? Well, this is the Badwater Ultra Marathon. Can you imagine running 135 miles, as if that wasn't hard enough, to do it in Death Valley, California, in the summertime? It takes place in the summertime in the desert. These people are crazy. You can see some of the records. These have probably been beaten since I first put this together. But what would be more of a test to our body's ability to thermoregulate than running an ultra marathon in the desert in the summer? No, thank you. Because of the extreme stress this puts on your body, these racers, these are real pictures from the race, will have a little support crew in a van where they can stop and cool off and take naps. And you can see that they're actually, many of them wear long sleeves to protect from the sun. But of course, those would be moisture wicking sleeves and not just good old-fashioned cotton. Very quick review. When we talk about thermoregulation, your body has to balance how much heat it produces compared to how much heat it loses. We want the scale to be pretty balanced almost all the time. What are ways that we produce heat? Simply by our everyday activities, our organs just functioning. They produce heat with our basal metabolic rate, our organs just doing what they need to do to keep us alive. The two that I'm going to point out here for exercise, when you exercise and your muscles are active, they produce heat. Heat is a byproduct of energy metabolism. Another thing that can be influenced with exercise is the environment. The hotter it is outside, the more heat you're going to produce. So ways in which we produce heat. Check it out, people. We only have 4 mechanisms to get rid of that heat. So for all the ways that we produce heat, we only have these 4 ways to release it. And under normal circumstances, we're able to get rid of that heat pretty well. Make sure you review the definitions. Radiation is just losing heat out into the environment. Conduction would be losing heat through direct contact, like sitting on a cold or hot chair. Convection is losing heat, in this case, losing heat as air or liquid passes over you. And then evaporation is sweating. We rely on all 4 of these when we're exercising. But let's get a little bit more specific. And of course, this is a picture that just shows us all the things that are happening during exercise. There are things that we are doing that are producing heat, but we also have to do things to get rid of that heat. Okay. Which heat loss mechanism is most active at rest? Radiation. And by the way, these things are also in your lab book. So of the 4 things, we utilize all 4 of them. But at rest, what are we utilizing the most? Radiation. What about during exercise? What heat loss mechanism is most active? Evaporation. So again, we rely on all 4 when we're exercising. But what do we rely on most during exercise? Evaporation. I have some other questions for you. We expect to have an increase in core temperature during exercise a little bit. So let's just look at, under normal circumstances, our internal core temperature should be somewhere around 37 degrees Celsius. And yes, we're going to use Celsius because this is a real science course. When we exercise, we expect that to go up a little bit. So with exercise, we're probably going to see 37.4 degrees. And maybe even a little bit higher. Maybe even 37.9 degrees. So we expect the temperature to go up a little bit during exercise. However, if our core temperature goes up too much, meaning that our body is not able to get rid of the heat that we're producing, it can lead to real problems. An increase in core temperature of 4 to 5 degrees Celsius can lead to serious dysfunction. So you should know that number. 4 to 5 degrees Celsius, an increase leads to real problems. In the real world, if someone's exercising and they get up to 40 degrees, oh my God, we're going to stop the exercise because that's a warning. So we're going to stop long before we get to that 4 or 5 degree increase. This can be deadly. It's not only temperature that matters too, it's also humidity. So make sure you review humidity. Humidity refers to the amount of water in the air. So not only does it matter just the dry temperature, but the amount of water in the air. So if we were in Albany versus in Las Vegas in the summertime, Albany is prone to being more humid. Las Vegas is not humid. So even though it might be 100 degrees dry heat, 100 degrees Fahrenheit, in Las Vegas, it could be 92 degrees here in the summertime, but because it's humid, it can feel warmer. But I want to talk about the physiology of it. And this is just going to be something for you to probably listen to. Unfortunately, you can't see me gesturing like I would if I was in real class. When we evaporate, that's sweating during exercise. When we evaporate, the moisture on the surface of the skin moves from high amount of moisture on the skin and it evaporates to low amount of moisture in the air. And this is the principle that we utilize in our body all the time. Things move from high to low, and it's no different here. In order for us to evaporate and sweat effectively, we have to have a higher concentration of water on the skin surface and a lower concentration of water in the air. When it is humid out, how does it change that equation? When it's humid out, we have more moisture in the air. And when we have more moisture in the air, it's more difficult to go from high to low. Even if we have a lot of water on the surface of the skin, we don't have as much of a gradient. Because now, let me do my trusty little eraser, watch me go. Because now, we may have a lot of moisture in the air. So we no longer have the gradient. And if we no longer have the gradient, things don't move from high to low. So we may very well, in humid conditions, the body will send fluid to the surface of the skin to try to evaporate. But because there's more moisture in the air, we're not as effective at evaporating it. Maybe you've had the experience of when you're sweating, but the sweat just seems to roll right off of you. That's the reason why we've lost the concentration gradient. Now, of course, if we spend a period of time in an environment, our body can acclimatize. And we can acclimatize to temperature, we can acclimatize to humidity, and we can acclimatize to altitude. This lab would only be talking about acclimatization to temperature and humidity. Make sure you review some of the things that happen when we acclimatize to the heat. So we're looking at acclimatization to heat only here, really. When you're used to the heat, you sweat earlier and you sweat more. And those are good adaptations. If I can sweat more and I can sweat earlier, I'm able to utilize more evaporation and get rid of more heat. Acclimatization changes begin as early as 48 to 72 hours. So if you have an event and you can get there 2 or 3 days early, you may have some ability to acclimatize, but really, if I want to have the best acclimatization, I want to stay there for 10 to 14 days plus. Ideally, it's like 2 or 3 weeks. So within 2 or 3 weeks, you're really going to get more significant adaptations and acclimatization. Okay, some last questions before we talk about the third part of today's lab. Are there differences in how different people, ages, body compositions thermoregulate? Absolutely. Who can thermoregulate better, adults or children? Adults. Adults have more surface area, so they have more skin surface area with which to sweat from. Adults have better developed sweat glands. So to all of you who are going to be, let's say you're coaching little Pee-wee in soccer, or you're coaching little Pop Warner football, it's not that kids are babies. They may need more water breaks because they're not as well developed in their sweat glands. They have less surface area to sweat from, so they cannot thermoregulate as good as well. So if you're having a practice in the summertime and you as an adult, you're okay, that doesn't mean that the kid is okay, because they are not as able to thermoregulate as adults. How about a big guy versus a little guy? It depends. If we're talking about fat mass, if we're talking about a big guy because of fat mass, if I draw a big guy because of fat mass, a big dude with fat mass has less ability to thermoregulate compared to a skinny dude. A skinny dude, that's my skinny dude, can actually thermoregulate better. So I think about like football players, you have linemen, they're big dudes. While it's a lot of muscle, it's also a lot of fat. They're not as able to thermoregulate. If you look at the deaths from heat stroke and what's happened in football, it's most often a big dude. Simply because that layer of fat adds a layer of insulation. And that layer of insulation means, first of all, it insulates, so it keeps heat in, but it also means that it's more distance for the fluid to have to travel to get to the surface of the skin. Lastly, men versus women. Drum roll, please. They can thermoregulate about the same. There might be small differences, but they can thermoregulate the same overall. But they do it differently. I'm getting excited, watch out. Let's talk about men. Men rely more on evaporation. Men will evaporate. They will sweat a lot. But you know what? Men tend to be wasteful sweaters. Good stuff, isn't it? So men are going to rely more on evaporation, so they send a whole bunch of sweat to the surface of the skin. But they're not as efficient as women as sweating. So they tend to send a lot of sweat to the skin and maybe only able to evaporate a little bit of it. What about our female friends? Our female friends tend to rely a little bit less on evaporation, and they tend to rely more on shifting fluid within the body. Because as we shift fluid, we can also shift heat. Heat moves with the fluid. So women rely more on shifting fluid around the body. And of course they do evaporate, but they're more efficient sweaters. So a woman may not sweat as much as a man, but that doesn't mean that she's any less effective. 40, 50 years ago, maybe even less, it used to be thought that women just couldn't handle the heat as well. But with the more current research, they can handle it just about the same. It's just that they do it differently. And not one is better or worse, it's just different. If I was in class with you, I'd talk all about this. I had an experience when I was running a marathon up in Vermont City, or in Burlington, the Vermont City Marathon, where I overheated. And I like to show my medical record form because it shows you what was happening. So right after finishing a marathon, my blood pressure was super low, my pulse was high, and my rests were high. I had a high core temperature, and actually it even affected my oxygen saturation. But you can see, they circled what was going on with me. lightheaded, fatigue, weakness, altered mental status. And if we want to, we can talk about this more when we get to electrolytes, because they also did a blood test and they measured my potassium and sodium. All right. But let's talk about the lab that you're going to do. Okay, this is part 3, the last part. Here we're looking at the effects of temperature on our ability to thermoregulate during a prolonged exercise session. And this time we're pitting men against women. Who did we use? Well, we used our same female endurance athlete who's 25 years old, but we also now got a 25-year-old male. And just like before, they were put on a treadmill and told to run as long as they could. Here's our man. Our female version was Greta. I think our male version is Edgar. Let's call him Edgar. So you can see we set it up. Here's my 25-year-old male, Edgar. And here he is in normal conditions. Normal conditions were this one. 21 degrees Celsius is about 70 degrees Fahrenheit. And of course, we looked at some different variables this time. This time we looked at these variables: cardiac output, systolic blood pressure, diastolic blood pressure, core temperature, sweat rate, skin temperature. Here we can see sweat rate and core temperature as an example of things that I selected. You can see a pill here, because how are we going to measure core temperature while someone's exercising? We have them swallow a pill a couple hours before. I have done this before, ladies and gentlemen. You swallow a big pill, and it's got a little sensor inside. And as I'm exercising, someone who's on the side has a little sensor unit, and they hold it up to my back. And it's able to, from outside the body, sense my core temperature. I think I took the pill 3 hours before, and that was to give it enough time to get down the GI tract to the stomach. Speaking of that, here I am. There I am with all the doodads and whatever, and you can see all sorts of things. I had skin electrodes on, and I had swallowed the pill. Of course, everyone asked then, what happens to that pill? Well, you poop it out. I regret to say that I didn't get my fingers in it or anything, but I gave a little glance to my poop for the next day. I didn't see it. So sad. All right, make sure you review these terms. We already know about cardiac output. We're going to measure blood pressure, and you may have seen blood pressure as 2 numbers, one over another, right? The top number is called the systolic blood pressure, and that is the blood pressure that blood exerts against arteries when the heart is contracting, versus diastolic blood pressure, which is the pressure the blood exerts during the period of time that the heart is relaxing. 120 over 80, 110 over 80 is said to be normal. And of course, the unit for our blood pressure for both systolic and diastolic is millimeters of mercury for both. We measured core temperature with the pill. We measured sweat rate, volume of sweat that is released off the skin per minute. If I go back to this, unfortunately, to my knowledge, and I just got my PhD in exercise physiology, to my knowledge, there's really not a great way of capturing all that sweat. So what we had to do is put a tarp on the bottom of this exercise session. And literally, we just weighed the tarp before the exercise session and weighed the tarp after. So we could estimate the volume of fluid that had fallen to the floor. But that wouldn't be good enough. We also had to weigh my clothes before and after. So I put my clothes on dry, having weighed them before, and then I took a nude weight. And then after I was done, we weighed the clothes wet, and then I weighed myself nude. All the things that we're missing because we can't be in lab. But not to worry, nobody would have had to have gotten naked. And we also measured skin temperature. Okay, so here's Edgar. We set it up, and then of course you can see these are some of the variables that we purposely put in there: systolic blood pressure and diastolic blood pressure. And then you'll see your results. Instead of it being a trained person versus a sedentary person, here we had a male in blue versus female in red. A couple things I want to point out. Most of the changes that we see during exercise happen in systolic blood pressure. We want that to go up a little bit during exercise, but we want diastolic to stay relatively the same. And you can compare the differences between males and females. Here we are at 70 degrees. That was our first trial. I think I missed this back up, but trial 1 was 21 degrees Celsius. It's about 70 degrees Fahrenheit. And look at trial 2, 33 degrees Celsius, which is the equivalent of 91 degrees Fahrenheit. So of course, things are going to be different if I'm exercising and it's 70 degrees versus 91 degrees. So we can see some differences in how long each person was able to exercise. And you'll also see some significant differences in blood pressure, core temperature, and sweat rate. For example, look at rest. Look at my sweat rate at rest. 4.8 mils per meter squared per minute. Okay, 4.8, 4.6. Look at 70 degrees. It was 4.8 and 4.6 at 91 degrees, 0.1. So even before they did any exercising, in 91 degrees, we were sweating already. And look, which gender sweats more? Is it men in blue or is it women in red? Who sweats more? Men. All right? Okay, so the last thing that you'll be able to do is, with this information, be able to answer questions. We are here to help you. Please email us with questions. If you're in MyLab, you can use the remind message. Good luck.